Okay, so now that we have all of our circle vocab, we're going to look at a couple theorems that are going to get you started, and you'll see these theorems used multiple times as you're going through the proofs of the other theorems. So the first one is we're going to look at what happens when a radius and a tangent intersect. So we're given here that AB is a radius of circle A and BC is a tangent to circle A, and you can see how the radius and the tangent appear to be perpendicular, and you probably noticed that as you were looking at the vocabulary. So we're going to go ahead and prove that. Remember that right now our definition of radius is just a segment's a radius if and only if one endpoint's on the center of the circle and one endpoint's on the circle. And then our definition of tangent is that a line is a tangent line if and only if it intersects a circle at exactly one point. It says nothing about it being perpendicular to the radius. So the fact that it appears perpendicular is a conjecture, and we are going to try and prove our conjecture. Okay, so let's see. We start out with a radius and a tangent. Well, what do we know? All we really know about radii and tangent are that all radii are congruent. We have a theorem that says that. We know that point B is going to be on the circle because AB is a radius, and so that means A is the center of the circle, so B has to be on the circle. BC is tangent, so B is a point on the tangent line and it's a point on the circle. But none of that says anything about angles that are formed. So this is actually going to be an instance where we're going to go indirectly. So we're going to do an indirect proof. And what do we do first in indirect proof? Well, first we have our indirect assumption. And our indirect assumption is that we assume that our givens are true. So we're going to assume that all of this is still the case. Our givens are true. But we're going to assume that our proof is false. What we're trying to prove is false. So AB is the radius of circle A, BC is the tangent to A, but AB is not perpendicular to BC. AB is not perpendicular to BC. Okay, so that means this is not a right angle. So it's either a little bit smaller than or a little bit bigger than the right angle. And ultimately what that means is that I can draw another line segment from A to line BC that is perpendicular. Right? Perpendicular lines are unique from a point to a line, but since AB is not the perpendicular, we can draw another line that is the perpendicular. So we just drew this. Get that on my line over here. So now we drew another line that's perpendicular. We will give that a name right there. That's going to be point D. And I'm going to hide those for us so we can tell what's point D and point B. Alright, so here's kind of my reasoning. Since segment AB is not perpendicular to line BC, we can draw a segment that is perpendicular to line BC, intersecting line BC at point D. So, point D is on line BC. This is important. It looks kind of like it's on the circle, right? But we didn't draw it so it was on the circle. We don't really know whether it's on the circle or not. All we know is that we drew it from A and we drew it perpendicular to line BC. And the fact that AB is not perpendicular to BC means that when I draw the perpendicular, it has to land at a point that's different than point B, which is what we are calling point D. All right. So remember what we want when we're considering a indirect proof is what we really want is to find a contradiction. Because this assumption right here, that AB is the radius of circle A and BC is a tangent to A, but AB is not perpendicular to BC, this is really saying there's a counterexample to our theorem. And so what I want to do is show that a counterexample is impossible by considering the counterexample and finding a contradiction, a geometric contradiction. Okay, So I'm going to do something a little tricky here. I know that there's a specific length between B and D. I'm going to replicate that length by using a circle. Alright, I might need to move this down a little bit so we can see things better. Yeah, there we go. Okay, so I'm going to use a circle and I'm going to put a point right here at the intersection of that line and the circle. So this is why I want to do this for you, because it's a little tricky. Alright, so what did I just do? And, oops. My computer's being a little slow on me. We would like to hide that circle. There we go. Alright, so we're going to put point E on line BC so that DE is equal to BD. Notice point E is still on line BC. Well, why the heck did I do that? Well, let's see here. If I draw that line right there, I know that DE and DB are congruent. So what does that mean? Well, that means that AD would have to be a median of this triangle right here, right? Because this is congruent to this, so D is the midpoint of EB. So this line AD is the median of triangle AEB. But it's also the altitude of triangle AEB because AD is perpendicular to BC. Well, if it's the altitude and it's the median, well, what does that tell us? It tells us that this triangle is isosceles. And so what that says is that this has to be congruent to this. So AB and AE are the same length, meaning B and E are the same distance from A. B and E are the same distance, they're equidistant from A. Is this a problem? I bet you can think of lots of different problems that we're getting to that would lead us to a contradiction here. One may be that, okay, the set of points equidistant from point A are all the points on the circle. And so what that would mean is that E would have to be on circle A. Right? If AE was a radius and AB is a or if B and E are both equidistant from A, they would both have to be on circle A. Okay, well, could E be a radius? Well, if AE was a radius, what would that mean about E? Well, it would mean that E was on the circle. But if E is on the circle, and E is also on line BC, right, because we know that E is on line BC, and B is on the circle, but it's on line BC, well, this contradicts that we have a tangent line, right? Because the tangent line can only intersect the circle once. So there's my contradiction. And you might have thought of a different contradiction. There's a couple different ways that we can go about doing this, but I kind of like if these are both equidistant, then E would have to be on circle A, but E cannot be on circle A because that would mean that BC was not a tangent line because it went through the circle at two different points. Therefore, because we found a contradiction, we know that a counterexample does not exist to this theorem. It is geometrically impossible to have a counterexample, so my original theorem must be true. The line that is, when a radius intersects a tangent, they form a right angle, or they are perpendicular. The radius and the tangent are perpendicular at the point of tangency where the radius and the tangent intersect. The converse of this theorem is actually much easier to prove. First, if I'm thinking, okay, now we're given that these lines are perpendicular and we want to show that BC has to be a tangent, we're going to do it directly as well. So we're going to assume all the givens are true. AB is perpendicular to BC and AB is the radius of circle A. But then we're going to say, okay, well this time we're going to say BC is not a tangent to circle A. Well, if BC is not a tangent to circle A, what does that mean? Well, that means that it either goes through the circle 0 times or it intersects the circle 2 times. Well, clearly, because we know B is on the circle, it can't intersect the circle 0 times. So what that means is it must be a secant line. It must intersect the circle twice. So that means there must be some other point on line BC that is also on the circle. Now you're going to see it's impossible for me to actually draw that, so you kind of have to use your imagination. So we're going to say, okay, well that means we have another point, we'll call it point F, that is on the circle and on the tangent line. Okay, so there's a point F, and we're going to say, okay, point F then could be on the circle. Point F is on the circle and on line BC. All right, now this is a problem. We already have our contradiction. It's very easy. We have a right triangle here, right? BAF. Well, what do we know about right triangles? Well, we know that the right angle is the largest angle in the right triangle. We also know that that means the hypotenuse is the longest side in the right triangle. This right triangle cannot be equilateral. It cannot be isosceles. AB and AF cannot be congruent. Well, it could be isosceles, but that would be FB and BA. But AB and AF cannot be congruent because of the side angle inequality theorem. We know that the side opposite the biggest angle has to be the biggest side, which means that by the side angle inequality theorem, AF is larger than AB, and that contradicts the fact that F would be on the circle. So we found our contradiction, which means that the counterexample does not exist, and our original theorem must be true.